last talk of the workshop. So we have Shubhangi Saraf from the University of Toronto in both math and computer science. And Shubhangi is also a co-organizer of the workshop. So thank you very much for organizing the workshop, and is an expert across many fields of complexity theory. And will tell us about that today. Thank you.
Thank you, Matt. Huge congratulations to Mark, of course. It's been amazing in this workshop to see the depth, breadth, impact of Mark's work. It's been really inspiring. I have never collaborated with Mark directly, but I've been fortunate to call him my friend. And I hope that as a result of this talk, I will tempt him to work on some questions in algebraic complexity theory. Okay, so I'll be talking about the complexity of factors of polynomials. And this is based on joint work with Somnath Bhattacharjee, who's in the audience here, my student, and with Mrinal Kumar, who used to be my student a long time ago, Shantanu Rai, Varun Ramanathan, and Ramprasad Saptarishi. Okay, so let me start with this very basic question. So suppose P is a polynomial. It's a degree D n-variate polynomial, and it has some number of monomials when you write it out as a sum of monomials. And D, N, and S are parameters. You could think of D and N to both be polynomially related, and S is some parameter. Think of S for now to be also polynomially related to D and N. And here's a question. Suppose there's a polynomial which has only few monomials. Okay, so S monomials, think of S as small. The max number of monomials is D plus N choose N. So that's exponentially large with N. But suppose your polynomial starts off having much fewer than that monomials. What can you say about the number of monomials in the factors of this polynomial? Maybe I said F, I mean P all along. Okay, so what can you say about the factors of this polynomial? If P can be written as F times G, can you, and P is sparse, is F sparse? And by sparse, perhaps one could hope to say that if P has few monomials, perhaps the factors have only polynomially larger monomials. Could one hope to say this? And it turns out that this is false. One can find polynomials, and on the next slide, I'll show you an example of a polynomial which has some number of monomials, but the factors have super polynomially many monomials compared to what P has. So in this strength, it's false, but we really don't understand the answer to this question. The best examples we have of polynomials where factors have many monomials, or the best blow-ups we have by examples, is very, very far from anything one can provably say about this quantity. So it's conceivable that if you have polynomials with very few monomials, the factors are still exponentially dense. And it's an open question, we don't have the tools. So here is an example by just an observation by von Surgatten and Kaltofen. So notice that x to the d minus 1, this has only two monomials, but this factor has d monomials. And by taking a product over, how does this pointer work? I'm not good at it. By taking a product over, take many different variables, and by taking a product over xi to the d minus 1 over many xi, you can create polynomials with more monomials. And if you, and then you can find factors with also many monomials. So if you work it out, you can see that if f has some number of monomials, you can construct polynomials where the factors have quasi-polynomially larger number of monomials than the underlying polynomial itself. So there's a quasi-poly blow-up in this example, which is not too bad. You could have had an exponential blow-up, but this example just gives a quasi-poly blow-up. And one can conjecture, and it was conjectured by von Surgatten and Kaltofen, that perhaps this bound is always true. You can't find polynomials where factors have a lot more monomials. And we don't know. This question is really wide open. Let me leave this question. If you play games with the degree of the polynomial and the characteristic of the underlying field, one can get bigger blow-ups. where you can have construct examples where the factors have a lot more monomials, but over the reals, this is about as big a blow up as we know how to get, and we have no way today of proving this. Okay, so this is a very interesting question whose answer I do not know. Here's another related question. Suppose your polynomial p, which is again degree d and n variate, you don't know that it has few monomials, but you know that it's computable using a small arithmetic circuit. Again, I'll define precisely what an arithmetic circuit is, but this polynomial is efficiently computable. What can you say about the factors of this polynomial? Are they efficiently computable? And before I answer that question, let me just tell you what an arithmetic circuit is. So an arithmetic circuit, my slides got a bit distorted when I transferred them over, but hopefully it won't be too bad. An arithmetic circuit is an object which takes in variables and constants from your field, adds them and multiplies them in some order. So computes a sequence of additions and multiplications and computes a polynomial as the output. And the size of the arithmetic circuit is the number of gates in the circuit. It's not the number of additions and multiplications you needed to perform. Yes, Bobby? Gates have unbound. So if you look at unbounded depth circuits, one can think of fan-in-two gates, because with a small blow up, you can make everything fan-in-two. But we'll also be talking a lot about constant depth circuits in the talk, and then we'll allow for unbounded fan-in. Thanks. Good. So for now, we can assume that let's assume that the fan-in of any addition or multiplication gate is an arbitrary polynomial in the number of input variables, so it's really arbitrary. The size of the circuit can be the number of wires in the circuit, if you prefer that measure. Every gate in the circuit computes a polynomial, and the output of the circuit is the polynomial that is output. This is so the depth of the arithmetic circuit is the longest path from the leaf to the root. The size of the circuit is the number of gates or the number of wires. It doesn't matter too much. We won't be looking at such fine-grained information. The degree of the output polynomial is the max degree of any monomial at the output. And some parameters related to arithmetic circuits. And this is an algebraic analog of Boolean circuits, where the gates were and, or, and not gates. Now you have multiplication and addition gates. And instead of computing a Boolean function as output, you're computing a polynomial at the output. And this is a very natural model for computation of algebraic problems. If the graph of the underlying circuit is a tree, you call this object an arithmetic formula.
So yes? No matter if the degree is kind of semantic or syntactic, does it make a difference? Or?
Good question. So so Mark asked, does it matter if the degree is semantic or syntactic? And by this, what Mark means is, suppose you're computing a polynomial of degree d at the output. Should the arithmetic circuit only compute polynomials of degree at most d along the computation? Or can you, at intermediate stages of the computation, compute very high degree polynomials, where the high degree stuff magically cancels out to compute a degree d thing at the output? So it turns out that for general circuits, it doesn't matter. To compute a degree d polynomial as the output, you can ensure that you do not have these cancellations and you don't go to much higher degree. But in different models of computation, like bounded depth arithmetic circuits, that's not true. So let me define the degree of a circuit as the maximum degree of anything computed along the way for now. For general circuits, it will not matter, but it does matter for intermediate computation. For the purposes of this talk, it won't matter. The distinction.
It would be even worse if you allow me to, let's say, destroy some gates and see what the degree would be to go even higher, right?
Right. The cancellations won't occur. Absolutely. So it could be like a circuit is computing a degree d polynomial at output, but yeah, but if you perturb the circuit, maybe you're computing an exponential degree thing. So in general, that could happen for an arbitrary circuit. For the objects I'm talking about, it will not arise, but this is an important point, and in a lot of work in arithmetic complexity, this distinction is quite important. Whether if you're computing a homogeneous polynomial at output, does it make sense to compute non-homogeneous things at intermediate stages, etc. Okay, so this was the question. So if suppose you have a polynomial in degree d n-variate computable by a smallish circuit, what can you say about the complexity of the factors? Are the factors low complexity? And this is a beautiful classic work of Kaltofen from the 80s, and the answer is yes. That if a polynomial f divides this polynomial p, then indeed this factor is computable by a small arithmetic circuit. And it's highly non-trivial. It's an amazing result. Such a result. So not only did Kaltofen show how the factors are low complexity, he also showed that there's an efficient randomized algorithm for computing all the factors. And this is all very non-trivial and really elegant math behind it. And like I mentioned, we don't know such a result when we don't talk about circuit complexity, but we talk about monomial complexity. So, yes?
I'm not sure how to interpret the randomized polytime algorithm on the bottom of your slide. Do you mean given a circuit diagram representing P?
Yes.
There's a randomized polytime algorithm that outputs algebraic circuit diagrams
Yes.
representing all
Yes.
the
Yes. Yes.
Wow.
And not only that, there's a follow-up both by Kaltofen and Traeger, which says even if you have a polynomial computed by a small circuit, and even if you can't see the circuit diagram, but the circuit is hidden inside a black box, and all you can do is evaluate the polynomial at whatever point you want, there's a randomized algorithm which will output black boxes for the factors, which is amazing. This is like really, really beautiful results. Okay, so you can do all of this. So circuits are really, there's a lot of nice math that goes into it, and we'll see some of it in the talk. And so circuits are very nice and robust. They have all these nice properties. The monomial representation doesn't have these properties because we don't know how to prove anything like this. So, okay. Okay, so some consequences of Kaltofen's results. One is it shows that you can do a lot of nice algebra with arithmetic circuits. They're a very nice natural model of computation. And it's also known that proving this closure result, which shows that if a polynomial is simple to compute by a circuit, then the factors are simple to compute as circuits. This closure result is the crucial ingredient to, or the glue to show that these two fundamental, the big open questions of arithmetic complexity are essentially equivalent. So proving lower bounds for arithmetic circuits and de-randomizing polynomial identity testing. You can show that one implies the other using Kaltofen's result. So let me elaborate on what these two big questions are. Sorry. Good. So I said this is the glue between the two big open questions of arithmetic complexity theory. So let me define loosely what they are. So Valiant in the 70s defined the VP versus VNP question as the algebraic analog of the P versus NP question. And so VP is the analog of P. VP is the class of polynomials computed by polynomial size arithmetic circuits. So those polynomials which have small arithmetic circuits computing them. VNP is the algebraic analog of NP. It's the class of explicit polynomials. And I don't want to describe it too carefully, but the permanent polynomial is complete for VNP. I'll just say this for now. And the VP versus VNP question is the question of trying to separate VP from VNP. Can you show or find an explicit polynomial that you can prove needs super polynomial size arithmetic circuits? So in particular, if you can prove that the permanent needs super polynomial size arithmetic circuits, you would prove that VP not equal to VNP. And in some formal sense, this is an easier and more structured problem than the P versus NP problem. To separate P from NP, you need to first show that VP not equal to VNP. Okay, so, and it's easier, more structured. Perhaps there's been a lot of exciting progress in the last 10, 15 years on the problem. So perhaps before we see any resolution of P and P versus NP, we'll perhaps get a resolution of the VP versus VNP conjecture. Okay, so that's the question of lower bounds for arithmetic circuits. Here's the question of polynomial identity testing. Suppose you're given an arithmetic circuit computing a polynomial. You want to decide, is that polynomial the identically zero polynomial? Can you do it? This is the Boolean analog of this problem is given a Boolean circuit. Can you decide if the function it computes is identically zero? So the Boolean analog is very hard. This is equivalent to SAT, and being able to decide the Boolean analog is equivalent to the P versus NP question, and it's believed to be really hard. This polynomial identity testing, the arithmetic analog, when you're given an arithmetic circuit and you ask, is this the zero polynomial? This is an easy problem. There's an extremely simple randomized algorithm for deciding if an arithmetic circuit is zero, which is just evaluate the circuit at a random point. And if your polynomial is zero, you will always, the evaluation is zero. If your polynomial is non-zero, then at a random point, it will take a non-zero evaluation with high probability. And so it's one of the problems where we have a really simple, nice, natural randomized algorithm, but we do not know any deterministic, no non-trivial deterministic algorithm for this problem. And I think it's one of the most natural problems for which we know such a nice, simple randomized algorithm, but nothing deterministic. Complexity theorists in general believe that this can be de-randomized. And this Kaltofen's factor closure for arithmetic circuits links these two problems, de-randomizing PIT and proving lower bounds. And in the beautiful work, Cabanets and Impagliazzo, this is from 2004, they showed that if you can prove sufficiently strong lower bounds for arithmetic circuits, this implies an almost complete de-randomization of PIT for these circuits. And this proof, which shows that one implies the other, uses Kaltofen's result. Okay, sorry. Questions? Okay. Very recently, Robert, Dipanshu, and Roy studied these trade-offs between PIT and lower bounds and proved even tighter connections between these two results. Yes, Bobby?
I remember a paper that had comments on that had almost a converse to this.
Yes, so there is an almost converse. There is a converse to this. So I didn't state that. So the factoring result is used in this direction, and there's an almost converse in the other direction, which is not as clean to state. But it is an easier to state converse, which is if you can de-randomize polynomial identity testing in the black box model, then there's an almost immediate converse to lower bounds to get shows that PIT implies lower bounds. But if you have it in the white box model, the statement's a little bit more messy to state.
Okay.
But the same paper has both directions. Okay, so in the rest of the time that I have, I'll talk a little bit about, we saw a little bit about complexity of factors, and I'll tell you a little bit of more that is known, and then I'll state some recent results and give a few ideas in the proof, and we'll see some applications. So Kaltofen's work showed that VP, so the class of polynomial size circuits, is closed under factoring. But people, algebraic complexity theorists, study all kinds of intermediate models. You can study arithmetic formulas, you can study arithmetic branching programs, so constant depth arithmetic circuits, which in the last few years, for various reasons, have received a lot of attention. You can ask it for sparse polynomials, you can ask it for VNP, like which of these models is closed under factoring, and there's been a lot of work on many of these. Till recently, we knew that branching programs are closed under taking factors. VNP is closed under taking factors. And there's some mild work for sparse polynomial and constant depth circuits if you can bound the individual degree of each variable by an absolute constant, even then we have some closure results, none. But what I'll talk to you about today, which is a very recent work from a few months ago, is that now we can show that even algebraic formulas and constant depth circuits, they're closed undertaking factors. And so here's the statement of the result. So pick any field f and let little f be an n-variate degree d polynomial. And suppose g is a factor of f. If your polynomial f was computable by a small arithmetic circuit of depth delta, then the factors of f are also computable by small arithmetic circuits, but the depth can be slightly larger. So if f was constant depth, then g is also constant depth. And this implies Kaltofen's result, the statement. And it also this also implies it for formulas. But if you don't see that, one consequence of our result is that if f is computed by a small formula, then g is also computable by a small formula. And our proof is clean enough, I think, and simple enough, and it gives a single unified proof of all the previous factor closure results that were known. So for circuits, branching programs, now formulas and constant depth circuits, but even for VNP, there's a border version of Kaltofen's factor conjecture, which I didn't talk about. But it's really one proof that ties, I think, all factor closure results that we know. So let me tell you, so since the main result is that constant depth circuits are closed under factoring, let me tell you a little bit about why constant depth circuits are so nice. One reason why constant depth circuits are nice is they're really expressive. So unlike in the Boolean world, where constant depth circuits, I think, are much more restricted than general circuits, in the arithmetic world, constant depth circuits are really can be quite complex. We know that if you understand depth 4 circuits well enough, if you can prove the optimal lower bounds for just depth 4 circuits, you will prove VP not equal to VNP. And that's because general arithmetic circuits can be squashed to depth 4 circuits. There are depth reduction results. And you can squash general circuits into depth 4 circuits without too huge a blow up. So if you understand even depth 4 circuits well enough, you are done in separating VP from VNP. Okay, so constant depth circuits have hence attracted a lot of attention because they seem like an easier class to get your hands on, but at the same time, they're still almost as rich as general circuits. And a breakthrough work from a few years ago by Limay, Srinivasan, and Tavanas gave the first super polynomial lower bounds for constant depth circuits. Prior to this work, we didn't have such results even for depth 3 circuits. There's been a lot of work on constant depth circuits, but the lower bounds for homogeneous constant depth circuits or other restricted versions of it, for the first time now we have super polynomial lower bounds for constant depth circuits, and strengthening these lower bounds would be amazing to get exponential lower bounds. And Chuo, Kumar, and Solomon, and these using hardness randomness trade-offs, we now also know the first sub-exponential time deterministic PIT algorithms for these circuits. And these PIT algorithms followed from the lower bounds by understanding complexity of factors of constant depth circuits. So the result I'm going to talk about is also talking about factors of constant depth circuits, but this was a much more specialized result for specialized factors of specialized form of constant depth circuits. By understanding those completely, one could still get some kind of trade-off between lower bounds and PIT. Okay, so that was the result. I am going to say a few words about the proof and then a little bit about applications. So before I tell you what works in the proof, let me tell you what doesn't work. So suppose I want to, before finding factors, let's see, suppose I just want to compute the root of my polynomial. So P was a multivariate polynomial, my X, X is a bold-faced X. Think of X as to being a tuple of variables. So suppose I want to find a root of my polynomial P of X comma Y. So if my polynomial can be represented as Y minus F of X times Q of XY, what can you say about the complexity of F? What we know is using the techniques we know, you use something like Newton iteration, and they compute these roots of a polynomial by this iterative process where you start with an initial, where you set X to 0, find an initial starting point, and then compute the roots to higher and higher degrees of accuracy. And if you can do this for enough steps, you will recover the root of F. I'm not talking in too much detail about it. There are some initial starting conditions which are important for this process to work. Your polynomial, if it should be square free and shifted suitably, but these are conditions that can be made to be satisfied easily. And there's an iterative process which once you carry it out for enough steps will give you the root of F. And this process shows you that if your polynomial P was low complexity, then and if in particular if P has a small circuit, then the root F has a small circuit. But the process is a sequential process and it blows up the depth along the way considerably. So that iterative process which I showed you, this is the reason the previous proofs broke down in arguing over the complexity of constant depth circuits. Because if P is constant depth, that process makes it very hard to analyze the depth of the factor F or the root F. But our result was enabled by one of my co-authors stumbling upon this amazing result by Furstenberg from the 1960s. This is the same Furstenberg who we heard in Subhash's talk, who works on ergodic theory and density Hales-Jewett theorem and Zemeredi's theorem, etc. The same Furstenberg in 1967 proved the following amazing result. He has a paper and he had this formula that we found in his paper that I think just the algebraic complexity theory community was not aware of. And this is the statement. It's a very simple, elegant, and mysterious statement. At least mysterious when you see it like this, but Furstenberg probably had a reason to come up with it. So here's the statement. So suppose P is your polynomial. For now, just think of a bivariate polynomial P of Ty. And we're again looking for roots of P. So we're looking for polynomials F, or looking for an expression for a polynomial F of T, where if P can be written as Y minus F of T times Q of T comma Y. So F of T is the root of the polynomial, if you view the polynomial as a univariate in Y. Then Furstenberg gave a direct one-shot formula for what F of T is. He said, you don't need to do this Newton iteration process. Here is a one-shot formula for what the root looks like. This is what it is. Okay, so let's understand what this expression is. So again, there's some initial starting conditions. Let's assume that F of 0 is 0, and at 0, F of 0 is a multiplicity 1 root of this polynomial. So some basic initial starting conditions, let's not worry too much about it. But under some basic initial conditions, you can get a one-shot formula for the root. So what is F of T? You take your polynomial P, which is a polynomial in two variables, T and Y. You replace T by T times Y. You take the Y derivative. You multiply it by Y square. You divide by P of Ty comma Y, and you apply the diagonal operator. Seems strange, seems mysterious, but let's accept it for now. And what is the diagonal operator? So this ratio you can view as a power series in T and Y. And then in this exponential power series, every term of the power series will have some T to the I times Y to the J times some coefficient. Let's look at all the terms where t and y, the t and y power is the same. And then pick out only those monomials. And then you erase the y part from it. And you just keep the t part. You just set y to 1. That's the diagonal operator. This is one short formula for the roots. Okay. So it's a one-shot description, no sequential process. We're going to use this formula for the roots and see what happens. And all the magic really lies in this. Once you take this magic formula and you plug it into, and now and with little bit of acrobatics with constant depth circuits, one can move along with this formula, gives you all the results we need. It sounds mysterious. The proof is shockingly simple. I think I won't have time today to talk about it, but it's really a one-slide proof of this result. So if anyone wants to stick around longer, I'll be happy to tell them. It's a very short, very elegant proof. Basic algebraic manipulations. It's literally on one slide, the proof of this result. Okay, but we did not know this. The community did not know this result, and I hope there'll be tons of other applications now that we know it. Okay, so let's take this formula and see what we can do. I stated this formula for when, oh, I can't go backwards. So I stated this formula for when your root looks like when f is a polynomial in T, but f could have been a power series in T in general. So if you're looking at arbitrary roots of bivariate polynomials, they can be power series. And Furstenberg's theorem holds, the same expression holds even for power series roots. Okay. So now what remains to be done? One is Furstenberg's formula was for bivariate polynomials. We are working with n-variate polynomials. That's one issue. Second issue, we still need to figure it out. Why does Furstenberg's result imply that if P had a constant depth circuit, then F has a constant depth circuit? We'll see that. And we just talked about complexity of roots of the polynomial, not complexity of general factors of the polynomial. So that's the third issue. So let me just quickly flash one slide for how to resolve each issue. Good. So one is you know how to deal with bivariate polynomials. How do you handle n-variate polynomials? And there's a nice trick for that, which is I had suppose my polynomial f was a polynomial in x1 to xn and y. Here's how I convert it to a bivariate polynomial. I multiply each of the x variables by a fresh t variable. And I view it as a bivariate in t and y. And I think of the x1 to xn coming from the coefficient field. So my coefficient field is this big field. My original field joined x1 to xn. So I'm working over this giant field, but now I have a bivariate polynomial. And as long as my original polynomial had some assumption that it was monic in y, by Gauss's lemma, you can see that the factors of the bivariate polynomial are in 1-1 correspondence with the factors of this n+1 variate polynomial. So I'm going to apply Furstenberg's theorem to now the new bivariate polynomial, but the field I'll be working over with is huge, but it won't matter. So that's how you go from n-variate polynomials to bivariate polynomials. Now I want to show you that if you use Furstenberg's that formula, and if your original polynomial is constant depth, why are roots constant depth? And so for that, let me tell you some things that one can do in constant depth circuits. I won't prove it, but these are some nice operations that constant depth circuits can do. So if you have a polynomial f, which is a small constant depth circuit, then the coefficient of y to the I in the polynomial f, that looks like some polynomial in the x variables. It turns out that the coefficient of y to the I, you can extract it as a small constant depth circuit using some kind of polynomial interpolation. So if your polynomial has a small circuit, then intermediate, you can view it as a polynomial in y, and the coefficients of each y to the I are small circuits. Once you have this, one can prove that if a polynomial has a small constant depth circuit, then derivatives of the polynomial have small constant depth circuits. Yes, Bobby?
So here, as you go from one book to another, the definition of small is allowed to get modified by
polynomial factors. factors of D, polynomial blow up. By small, I just mean polynomial in the input circuit. And so, yeah, so if f has a small circuit, the coefficient of y to the I has a polynomially small, polynomial in the complexity of f constant depth circuit. If f has a small constant depth circuit, then the y derivative of f has a small constant depth circuit. And by the previous bullet, you can reduce this and you'll pay for some other polynomial factor. And here's another more non-trivial result, which I won't prove to you, which is that if f and g have constant depth circuits, and if g divides f, then this ratio has a small constant depth circuit. And if f doesn't divide g, then you can express f over g as a power series where the coefficients of the power series have small constant depth circuits. Okay, so I'm just stating these as facts without proving, but none of these individually are very hard to prove. So now let's go back to Furstenberg's that expression and see why, if the polynomial p has a small constant depth circuit, why should we expect f of t to have a small constant depth circuit? And it's not so hard to see at this point, given what I have just told you. Notice that we're thinking p has a small constant depth circuit, but we're thinking of it as a small constant depth circuit in this giant field of f adjoint x1 to xn. So that is in the background that we have these, each p is, when p is a bivariate polynomial, the coefficients of each monomial are constant depth circuits. But step by step, if p has a small constant depth circuit, by the previous slide, the derivative has a small constant depth circuit. The ratio can be written as a small constant depth circuit. Even if it's a power series, all the coefficients have small constant depth circuits. And this diagonal operator also maintains this property of having small constant depth circuits because it's pulling out certain monomials in this big expansion, which you can recover by interpolation, which can be carried out by small constant depth circuits. So that's all I'll say about it. So if you really go, use the properties I said, and you open up this expression and understand it, it's not very hard to see that f of t also has a small constant depth circuit. And we're almost there. So what remains? This almost gives us this property that the roots have small constant depth circuits. Why do general factors have small constant depth circuits? And the reason is the following. Okay, so first, here's a fact. Just from general algebra, this is not our contribution. This is just saying that take any bivariate monic polynomial such that at t equal to 0, it's square free. Then you can express your bivariate polynomial as a product of degree 1 factors of the polynomial. Okay, so you can express the roots of this polynomial as power series in t. So you view this polynomial as a univariate in y with coefficients coming from f adjoint t, and each root can be expressed as a power series in t. This is just in general. This expression exists for all polynomials. The Newton iteration formula I gave you a few slides ago gives you a way of computing these power series. But even Furstenberg's theorem now gave you a way of calculating these power series. Questions? Because I see some puzzled faces. Yes?
Algebraically closed, so y splits into linear factors?
Good question. So I said let z be the roots of f of 0 y. So this expression sits in the algebraic closure. Yes. So my underlying field may not be algebraically closed, but this expression right now, the coefficients of my power series are in the algebraic closure. Because I set t to be 0, I got a univariate in y, and I took, for this univariate polynomial, I said, okay, let z be the set of roots. So to get the roots, you have to go to the algebraic closure. My final statement, my final result will not go to the closure. But as an intermediate step, we will see that you need to move to the closure prove some things, and then when we talk about factors in the original base field, we won't have coefficients coming from the closure. But this is still just as an intermediate step, let's consider this expression where we do go to the closure.
In positive characteristics, I have to worry with
so I assume yes. So good. There are some things to worry about for positive characteristic. The statements that I made, so over characteristic 0, everything holds. And over FP, over characteristic P, you have to be careful. It's only known, even Kaltofen's results. This is a subtle point that I didn't talk about. All factors we don't know have small circuits, but a suitable pth power of that factor has a small circuit. So we don't know how, the following is an open question. Over characteristic P, if F to the P has a small circuit, does F have a small circuit? And this is an open question, even for circuits. So that is a slight technicality or an issue that we do not know how to resolve over. Over characteristic 0, everything is fine. Over FP, there's some subtleties. Okay. Good. So there is this expression, right? You can write F as a, I don't have too many minutes left. You can write F as a product of y minus p alpha of t, where as you range over all the different alphas, you get all the power series roots of F. And every true factor of F looks like is of the form, let's take a subset of these roots. So let's take a subset S of Z, and let's take the product of y minus phi alpha of t for alpha only in S. So every factor of F is of this form. Okay, so once I know that roots have small complexity, any factor is of this form, and I need to show that this expression has small complexity. But when I say that the roots have small complexity, these roots have small complexity as power series. So the coefficient of t to the I will have smallish complexity. But these are infinite power series. So, but a true factor would take these infinite power series, pick some subset of them, and when you take this product, everything cancels out and you get a true polynomial. And so if there is some subset of these phi alpha of t's that you can sample, where the product makes everything cancel out and you get a true polynomial, it's not hard to see that to compute this polynomial from these phi alphas, you do not need to look at you can truncate the power series at some high enough accuracy, and that suffices, because powers of t of very high degree won't contribute anyway. So you can look at truncations of these power series to compute your original polynomial. And that's essentially enough. These truncations of the power series have small constant depth circuits. And then a product of small constant depth circuits is a small constant depth circuit. And so the factor you're looking for will have a small constant depth circuit. And as Bobby pointed out, my phi alphas did come from the algebraic closure. But maybe I was looking for factors in the base field. So this expression right now still has elements coming from the algebraic closure, but I might be computing something which is in the base field. So there's one more step which I'm not going to talk about, but with a bit of extra work, one can symmetrize this expression and get rid of elements, the terms coming from the algebraic closure, and get everything to sit in the base field. Okay, so I don't have too many minutes left. Proof of Furstenberg's results, I think I won't have time for, so I'll talk about it later if anyone's interested. Okay, so it's an elementary, I'll flash the one-page proof. But let me, in the remaining couple of minutes, just give a flavor of the kind of applications we can get of our result. So one application is the following. We get better hardness randomness trade-offs for constant depth circuits. So now we know results like if you have exponential lower bounds for constant depth circuits, you can almost de-randomize PIT for constant depth circuits. If you have exponential lower bounds for algebraic formulas, you can almost de-randomize PIT for algebraic formulas. So we get strong hardness randomness trade-offs. And it's basically directly plugging in, going to the Cabanets-Impaliadze original proof and plugging in our results, and these trade-offs just follow. That's one application. Another application is we get the first deterministic sub-exponential factoring algorithms for constant depth circuits. Okay, so I'm rushing it a bit, but till now, we didn't, given a sparse polynomial, here's the question. Given a sparse polynomial, decide if it's an irreducible polynomial or not. We had no non-trivial deterministic algorithms for this, and our work implies the first deterministic sub-exponential time algorithm for it. But in general, we can get the first deterministic sub-exponential time algorithm for factoring constant depth circuits. Okay, that's application 2. Application 3. Good. So symmetric polynomials are those which remain invariant under permuting the variables. Elementary symmetric polynomials are a well-known subclass of all symmetric polynomials. And the fundamental theorem of symmetric polynomials says that every symmetric polynomial can be written as a polynomial of the elementary symmetric polynomials. And a very nice result by Blazer and Jindal from a few years ago tried to study the complexity theoretic version of this question, which is if your polynomial has small complexity, if you have a symmetric polynomial of small complexity, and you write it as a polynomial in the elementary symmetric polynomials, what is the complexity of that polynomial? And they showed that if P has a small arithmetic circuit, then Q has a small arithmetic circuit. So if you write it as a polynomial in the elementary symmetric polynomials, that composing polynomial Q has small complexity, and we can scale down this result. We show that if P has a small constant arithmetic circuit, then Q has a small constant arithmetic circuit. Okay, so that's another consequence. And last application, application 4. There was a recent amazing result by Andrews and Vigdison, which shows that the GCD of two polynomials can be computed in constant depth. And it's a really beautiful work. This can be, you can think of it as a GCD of two univariate polynomials can be computed in constant depth, but as a consequence, they show that the GCD of multivariate polynomials can also be computed in constant depth. But their results only work for fields of large enough characteristic. As a consequence of our work, we can make it work over fields of all characteristic. So we give a different modification of their proof and tweak a few key places to use a result on symmetric polynomials from the previous slide, and we can make this work over on characteristic. And let me not say more, just that everyone has had a long day. So I did ideas which went into the GCD proof, but I'm going to skip it. I think we've all had a long day. Let me flash the one slide proof of Furstenberg's result. Okay, so I wanted to prove that if the roots of a bivariate polynomial have this simple, nice expression, one shot. And so P of Ty is y minus phi of t times Q of Ty. Let's take derivatives of both sides, apply chain rule, not chain rule, the F times G rule, and divide both sides by P of Ty. So you apply the product rule, just do a basic division, replace T by T times Y, pre-multiply by Y square. Look at this basic algebraic manipulation. And now once you have this expression, let's take this diagonal operator of, which is an additive operator. So apply the diagonal operator and now stare at the expression. So on the left side, this is exactly Furstenberg's expression. We stare at this and see that it's easy to see this is 0. If you look at the power series expansion of this, it's going to be easy to see that each monomial has y degree strictly greater than t degree. So this will contribute nothing. And let's look at the power series for this. So this is 0. And if you look at the power series for this and you stare at it, then you can write this power series as a sum of individual of phi of terms of that kind. And you notice that, okay, everything has y degree more than t degree other than the setting when I equals 1 in that expression. I'm just going to keep it up. You just stare at it. You just stare at it. Just look at, just observe the monomials. Notice that you'll always get y degree more than t degree unless, y equals 1. Or maybe t degree more than y degree. You'll always get perhaps t degree more than y degree unless y equals 1. And then so I equals 1 is the only setting where there's any contribution, in which case you get the diagonal of phi of ty, which is the same as phi of t. That's really the whole proof. Very, very elementary, nothing going on. Okay, so I will just end there with some open questions. So I think it's a great question to ask about factors of sparse polynomials. We really do not, we have huge gaps between upper bounds and lower bounds there. Similarly, we know deterministic polynomial identity testing for sparse polynomials, but we don't, because we don't understand the complexity of factoring sparse polynomials, we don't understand the complexity of deterministic factoring algorithms for sparse polynomials. I didn't talk much about this, so let me leave it out. But here's another amazing question, which I briefly mentioned. Over fields of characteristic P, if you know that F to the P has a small circuit, what can you say about the complexity of F? I think we don't have counterexamples. F should also have a small arithmetic circuit, but we don't know how to prove it. So I will end here. Thank you.